Welcome. Today we're going to talk about curl and divergence. And I put here as a little subtitle, we're talking about descriptive tools for vector fields. So what do I mean by descriptive tools? So in general, in calculus, it's this, I always say this to students, is that it's the study of functions. And we need ways to describe functions. So that's this as a descriptive tool. So also calculus is tools for problem solving and a bunch of other things. They give us all the main ingredients to solve differential equations. But at heart, we have this. We want to use these tools to describe things. So it helps us describe very complicated things. So of course, generally, if we have some function f of x, it's a single variable function. The first tool we learned was that of the derivative f prime, right? And we know that that gives some information about what f is doing, and it gives the idea of a slope. All right. Now, in high dimensions, or in 2 and 3D, we learned other such tools. One was the gradient. So, for instance, in 2D, we have f of x comma y. If we can, so that defines some sort of surface in space, in two-dimensional space. Now, if we take the gradient of f, if here's our surface, we're looking over the top of it, and I'll make a contour plot. So let's say we have a very high point, and then we have sort of contours moving out along there, like that. All right, so this is f, and that's on the x-axis, and there's the y-axis, right? And f is, so that's the very high point of the function on the z-axis. So think of the z-axis as coming out of our screen here. And the idea of a gradient, what it does is that it produces a vector that points in the direction of steepest ascent. So for instance, if I'm sitting right here at my point x of y, it's going to point in the direction going more or less locally in the direction that's going up the hill, if you will, from that point. Now if I were over here, the gradient would point that way, and so on and so forth. All right, so that's one, and so this is a very nice descriptive tool. It tells us something about the surface that we're dealing with. All right, so I'm going to formalize this idea of a gradient. We're going to talk about the gradient as the gradient operator. All right, so I should before I talk about it as an operator, I'm going to define. Well, I'll define the operator in 3D. And here it's a partial derivative of x. It's the vector function, a partial derivative in y, and a partial derivative in z. Okay. All right, and this is the 3D version. Now, obviously, we can also define a gradient, and has it a similar notion of steepest ascent if we're talking about a three-dimensional function, and here's our domain, let's say. We can think of f then as like a concentration of some, or a density of some particle in space. So if in one point of space there's a whole lot of this one quantity, think of it as a kind of like a cloud. If I'm at a point over there, the gradient vector is essentially going to point towards that higher concentration, right? So that's the idea of the gradient there. So if f is the concentration, the gradient will point towards that. Again, another useful tool for describing either volumes or surfaces or functions in 2D. And so this gradient operator is incredibly important. It's a wonderful tool for helping describe things. And it works much the way a unidimensional derivative does, as it effectively talks about the slope. All right, so that's a lot of background. So what are we going to do with this? So now our goal is to study, our current goal, what we've been studying in this course now, is a study of vector fields. right? So vector fields, we're talking gravitational fields, electric fields, magnetic fields, things like that. It could be also a velocity of fluids flowing through space. So many examples of vector fields. And so we want new tools, some other tools to study vector fields. And the two tools are that of the curl, and the other one is divergence. So let's get, before we actually define them, I'll just say, what the basic gist of this is, what the take-home message, I'll say right this, is this will measure or describe the vorticity at, an XYZ point. XYZ, okay? So how much something swirls around some point, right? That's the idea. So we'll make that concrete in a second. And divergence, it will measure or describe a degree of expansion at a point. So the idea here is that at a particular point, we want to know how much the vector field is expanding at a point, or how much it's sort of like there's a pressure that's building out. Or it could go inward, right? We could have like it go the other way. The idea is we want to get some idea of the net expansion of the vector field about every point. All right, so these are really neat. Sometimes we call that the compressibility. Or we'll call this the curl. Okay. All right. So let's now define these operationally, and we're going to do so in terms of our base operator, which is the gradient operator. So let's do that now. Okay. Next page. All right. So let's talk about the curl. So we're going to define the curl as the gradient vector now crossed with our vector function f. So again, we want to know something about f. We're given some vector field f, and we want to use this new descriptor to describe what's going on here. So let's see if we can get some understanding of what this is. So we'll define this. This is going to be, of course, f. We can write f as a three-dimensional function, so it's going to be p of x, y, z, q of x, y, z, and r of x, y, z. Okay. So that's the function right there, and it's a vector function. And so and I'll again write down what our gradient operator is. So it's not, there's no functions in here, but it's going to be the partial with respect to x, the partial with respect to y, and the partial with respect to z. And now the cross product, we have to remember what this means. So what we define this as the curl. We usually put our f there as an input. And let's say, remember the cross product, when you put two vectors into a cross product, you get out another cross product. So this is or you get out another vector. So this really is a function from R3 to R3. So the output is another vector. All right. So we can write this down. This is going to be our vector, our unit vector in the x direction, a unit vector in the j direction, and a unit vector in the a unit vector in the y direction and a unit vector in the z direction. This is going to be our partial with respect to x, partial with respect to y, and our partial with respect to z. This is going to be p, q, and r. Okay, so we'll write this out. We have I, it's going to be, and I'm going to use a little notation just to simplify my thing. I'm going to call that I'll use that as my symbol for partial of x. This is my partial for y, and that's my partial for z. That's just another way of writing it. It's a little bit more compact. So I'm going to go, so we're going to talk about, do the partial with respect to y. So for the I, we have to do this matrix minor of R minus the partial of z with respect to q minus j. We take the matrix minor of these two, which is going to be the partial with respect to x of R minus the partial with respect to z of p plus k, which is the partial with respect to sorry, change that, partial with respect to x of q minus the partial of y with respect to p. Notice here, that's the part of Green's theorem. This looks as familiar from Green's theorem. Okay, well, remember that was part of the Green's theorem, and Green's theorem was if we have a closed circle, a closed path that we're going to integrate over, and we have to integrate over the interior, and it's going to be dA. All right, so that part shows up there. So we see some familiar objects built inside this curl, and in fact Green's theorem really is an expression of what the curl can do for us. And that was in 2D, so we can think of the curl as a generalization of some of the same ideas as what we discovered, or what we were discovering with Green's theorem. All right, so this is how we calculate it. The question then is, how do we make some meaning out of it? But before we do that, so let's talk quickly about that. So one way to think about curl is that I said it measures the rotation of f, our vector field, about whatever point we're interested in. Okay, so what we're doing is what we think about when we think about the curl. So it creates a vector, right? So this is some sort of output vector here. And what does this vector represent? So if I'm at a point x, y, z, and if the vector field around it has a sort of vorticity, there's some sort of swirling going around it, one would expect if I were to perform a work integral, a path integral around that point, I would get some non-zero value out of it. So let's say I do some path around x, y, and z, right? So that's my path, and I'm just going to put this in parenthetical. So that's what my work integral. I'm going to do some work about that by doing a path around there. And if the vortex, if the vector field has a sort of vorticity about this point, one would expect that this work integral will be non-zero. All right. So so it really is a measure of that work that you have to do going against or going with the vortex around that point. And so a good way to represent that is then with a vector coming perpendicular to the path that we've taken. So that will be what we define to be the curl of f. So what it represents then is is an axis about the rotation of f at the point x, y, z. All right, so so really that's operationally what that is. So the curl is a vector that sticks. It'll be perpendicular to the net vorticity around that point. So of course we could have lots of things going on. This vector field could have other components to it besides just the vorticity. But what it does is it really extracts from the vector field the part of the vector field that is sort of swirling about that point, and it measures it by sticking a vector going in the orthogonal direction. Okay, all right, and we're using the right-hand rule. So here's our finger, and our thumb sticks up like this. So if we have a counterclockwise work integral going around, and the vector field is parallel, or the vorticity of that vector field is parallel with that path as we go around, that means the curl vector will be pointing up, as with the thumb right there. But however, if the vector field were going the other way, if the vorticity were going the opposite way, we'd have the curl would be pointing down on the other side. Okay, so that's the general measurement that we're talking about here. So now let's talk about the divergence. Okay, so divergence, we often call this div of our vector field, and it will simply be the sum of partial of p with respect to x plus partial of q with respect to y plus partial of r with respect to z. And remember that f is the vector field defined by the functions p, q, and r. Okay? All right, so this is a pretty straightforward one. Now note also that this is a function that inputs go from R3, but the output is not a vector like the curl. The output is a real valued function, just a single value. So this is a scalar. All right, again, this will measure the amount of expansion of the vector field, and that's what we said. So, so how do we get some idea of what this is? So when I mean it measures the expansion of f at a point x, y, z, the idea here is we can think of it as like putting our point x, y, z inside of a box. And if we think of f as like a vector field of the velocity field of a fluid, we can think of it as if basically inside this box, surrounded by this point, there's some net flux going out through the box there, a net flux going out through the box there, and the amount going all out there like that. And the idea is it measures up the amount that's coming out. And this would be what we call a positive. If all the arrows were pointing out, we would have a net positive flux coming out of that box, and that would imply then that the divergence of f is greater than 0. So if the net, if the point, if there's some expansion coming out, but there's also some coming in, what we say there is that the divergence of f is 0, and we call that incompressibility. So we say if the field, the vector field f, is incompressible, it implies then that the divergence of f is equal to 0. And that means that basically if there's things coming out of a region of space, there must be coming out of the region of space going this way, there must be some other path where some fluid is coming into the space that balances that perfectly, and there's no buildup of pressure. So there's no so water is fairly incompressible, and so water is considered a type of fluid that when water is flowing in any region of space, the amount of water coming out of a region through maybe the sides through some direction. There's some other fluid coming in from a different side. Okay, so that's what we mean by incompressible. So you can see now that this is these tools that we're developing really are truly very descriptive. They really help us talk about vector fields, oftentimes in terms of velocity fields of fluids. How fluid is flowing around in space is usually how people discuss or conceptualize these notions of divergence and curl. All right, so so we have the definition here, but I want to write it down a different way. We have the divergence of our vector field. We can also write it down as the gradient operator, a dot product with our vector field. So again, now we have one. Just to review, we have a gradient operator crossed with f, and that's a three-dimensional to three-dimensional function, and that describes the vorticity. And two, or the circulation around a point in space. And then here we have the gradient operator dotted with f, and that is a input, of course, is always a point in space, r3, but here the output is a scalar valued function. Okay, so those are our two new descriptive tools for vector fields. Let's now let's go over a few examples. Something that can, before we go over examples, we have to talk about some fundamental relationships here. Okay. So one of these relationships, so I'll put this in A, is that gradient fields are irrotational. So that's what we call irrotational, is what we call it when curl of f is equal to the zero vector. Okay. So what do we mean by gradient fields? We mean vector fields that are a gradient of some potential function. So again, this is a mathematical identity that you can check yourself. Pretty straightforward to check this, and that's just that the gradient operator crossed with a gradient vector defined by a potential function, and this works for any f, okay, is always going to give you the zero vector. So you can check this yourself. It's pretty straightforward to do. It won't take you too much work. Okay, and another really important identity is what which is that curl fields are incompressible. All right, so that means that the divergence of any vector field that can be written as a curl. I'm going to actually edit my, I should say that the divergence of my curl is always going to be zero. And you can check this as well. It's in the book that you have. It's in any calculus book that you could pick up. And again, it just takes a few lines to compute this. So these are really nice relationships, and they tell you a lot about these fields, the properties of vector fields. All right, so now let's go over some examples to kind of illustrate what's going on here. So let's talk about, we'll talk about example 1, which is going to be a constant field. A constant field, so I'm going to give you a particular example. We'll talk about f is equal to 3, 2, 1. All right? So that means now if I write this, so I'll just write out some Cartesian axes here. So 3 on the x, 2 on the y, and 1 on the z puts me somewhere there. So I can put my little arrow. So that's going in space, and everywhere in space we have the same vector pointing in the same direction with the same magnitude. So if this were a fluid, this would be a fluid flowing, evenly, or in a laminar way. That's another way of calling it. But so when we think of fluids flowing evenly, so when we're thinking about our curl and our divergence, so is there any rotation? And the answer, of course, just intuitively is no. So you'd expect then that the curl of f is going to be 0. And of course we can check that quick. So we can write down our curl, which is going to be the determinant I, j, k, partial x, partial y, partial z, and then 3, 2, 1. And of course, all the derivatives of constants are all zeros, so it has to be the vector, the 0 vector. All right, and that makes perfect sense. If all the vectors are pointing in the same direction, there's no rotation, and no particle in this flowing in this kind of fluid is going to be rotating anywhere. Okay, so what about compressibility? So what about So the divergence also of this vector field should be 0, right? Because at any one point, there is some, you can think of any point in this space, there's a flow going that way, but some other point just upstream for it is flowing into it. So whatever is going out is also, there's some other thing going into that same region. So we expect the net divergence to be 0. And we can check that as well, and that's really straightforward. So again, this is the gradient dotted with f, and that's of course and of course the derivatives of constants are always going to, oh sorry, I'm messing up here. These need to be pluses throughout all of this, and that needs to be a round bracket. Okay, sorry, I messed up on my definition there. That's better. So the derivative of 3 is, of course, 0, plus the derivative of 2, which is another constant, plus 0, and that's equal to 0. Okay, so that's our very simple example. So now let's talk about some other examples, ones that we've studied before. I'll get myself a new sheet of paper here, just so I don't run out. And that is of a vector field we've seen before, and so this is example 2. And I'm going to do example 3 in the same page. We're going to talk about two vector fields that are related to each other. And one is going to be 1 over r times negative sine theta cosine theta. Okay, and we can rewrite this, of course. We've seen this before, and it's going to be, oh, sorry, one thing. We're talking about in 3 dimensions. This is a 2-dimensional vector field, as I had written it. But we can always transfer to higher dimensions by just saying that it's 0 in the z direction. And that'll just mean that at every point in the z-axis, what we have is a vector field that looks like what it looks below it and above it. So this is, if we rewrite this, this is negative y over x squared plus y squared, x over x squared plus y squared, comma 0. All right. So our example 3, which we'll write on this page, is going to be a little bit different. We're going to call our vector field. It's going to be very similar to this one, but without the 1 over r dependence. So it's going to be just negative sine theta cosine theta comma 0. And we can write this as root x squared plus y squared all over negative y over comma x over root x squared plus y squared comma 0. All right, so these are very similar vector fields, and if you can think of them, I can write them kind of side by side here. This one's going to have that 1 over r dependence, so as we go further out on the away from the origin, we'd expect the vectors nearer the origin should be bigger than the vectors as you get further away. And we see we have that sort of vorticity that we were wanting to talk about before. So we have something we can really study here. Okay, so at the origin there's a singularity. We have a singularity in the amplitude of this vector and also in the ambiguity of how it's swirling around. So points really nearby are going like this with a really big vector. So you expect there's a really high amount of swirling right around the origin. All right, so and for this one, for example, 3 here, what we have is we don't have any amplitude dependence, but we do still have a singularity. We don't have an amplitude blow up, but we do have a singularity near the origin. What we have here then is everywhere in space we have this swirling, but the magnitude of the vector, no matter where you are in relation to the origin, is always the same length. It's always length 1, right? So we have this swirling going around like that. Okay, so let's now discuss what's going on with these two vector fields. So we've already talked about this one earlier, and we knew that if we have a path, a circle, not around some sort of a closed path, as long as it wasn't wrapping around the origin, then the work integral that we compute in the two-dimensional path, we can write it like this. We can use the Green's theorem, and we knew that that component, this relationship here, was 0, so we knew that it was always 0. Okay, so this is an expression of something that it's curl-free, or what we call irrotational. All right, so we can't define the curl at the origin because this thing, the vector field isn't defined at the origin, but anywhere else but the origin, we can state that this is irrotational, and I'll just verify that fact. So we have to do the computation on this. So it's oh, sorry, it's not curl free. It's hold on. Never mind. Sorry about that. I made a little mistake. I misspoke. It truly is curl free and it's irrotational. And let's go verify that fact. Okay. So we're going to write down our curl, and it's going to be I, J, K, partial x, partial y, partial z, and then negative y over x squared plus y squared, x over x squared plus y squared, 0. All right, so we can write this. We find out quickly enough, and I'll skip through some of the parts here, that the first two components are indeed 0. Right, and that just left the last component, which again is, remember this right here was P and that was Q, which was, and the last component of the curl is always partial with respect to x of Q minus partial with respect to y of P. And we verified from before that that was 0. So indeed we have 0, 0, and 0. Okay. So the next thing we want to check then is what about the compressibility? And so we want to take the divergence, and so let's do that. So, so what we have to do then is now take the partial of x with respect to p, the partial y with respect to q, plus the partial of z with respect to r, which since r is 0, that's also, we can write that as 0, and that's the divergence. So we can quickly do that. So we take the derivative with respect to x, we're going to get a negative 2xy over x squared plus y squared, quantity squared. So that you can get that from the product rule, or from the quotient rule, sorry. And then we're going to add it to the derivative of this function, the q function, with respect to y, and then you'll get a positive 2xy all over x squared plus y squared, quantity squared, plus 0. And of course, you'll see these two terms are the same, so they're 0. So although this vector field appears to be getting smaller out here, right, and going in this direction, it appears that at every point here, whatever's leaving at that point, something else is coming in that's about the same. And there doesn't seem to be much lateral motion through this point. So it is a divergence-free medium. They also call this divergence-free. You're going to hear lots of, so when you go later on in your courses, you'll see these terms thrown around a lot. They'll talk about a fluid or some medium or some vector field as being divergence-free, and they mean that. So, so that's the take-home message for that vector field. Now let's study this one, which seems to be better behaved. We don't have this 1 over r dependence that we have, so the vectors don't get weaker and weaker as you go further out from the origin. So we have instead this swirling around the origin that seems to be constant. So let's discuss what happens here. So we can compute this this curl. So we'll talk about the curl here. So curl of f. And we're going to write that down over here, and that's going to be the determinant I, j, k. It's going to be partial x, partial y, partial z, negative y root x squared plus y squared, x root x squared plus y squared, all right, and 0. And just like before, we know that what will happen is be the first two components of this vector are going to be 0, 0, and then we'll compute that in a second what that is. All right, so we know that's what it is. So let's just go focus then on this matrix minor to compute this final one here. So we have to take the partial with respect to the partial x with respect the partial of this of q with respect to x, and the partial of y with the partial of p with respect to y. So that's what we're going to compute there, like that. And so let's do this one here. That will be, we need to do this with respect to x, so we have to do the product rule, or the quotient rule. So the derivative of x is 1 times root x squared plus y squared, minus, and we leave the x there, and we take the derivative of this, and we end up with, after doing the chain rule. And then of course we have to square the denominator. We get an x squared plus y squared. All right, that looks good. And now we need to subtract it from the partial of y. So we have to do this one now. So we're subtracting, and then we have the derivative with respect to y, so we're left with a negative 1 times root x squared plus y squared. And then we go subtract, which becomes a plus y over root x squared plus y squared all over x squared plus y squared. All right, so now when you do the math on this, and if you just keep working at it, you have to rationalize some denominators and do a bunch of stuff, but what you end up with is x squared plus y squared all over x squared plus y squared quantity squared, which becomes 1 over x squared plus y squared. So the curl of f in this case is going to be it's going to be for every point here, any point of a given radius around the circle, the magnitude of the curl is going to be equal to 1 over r squared, because that's what that is. That's r squared, the distance from the point to the origin. All right, so that's interesting. So here there was no swirling around the axis here because it had this 1 over r dependence in the vector field. But when we take out the 1 over r dependence, all of a sudden we get some vorticity around every point, and it's proportional. That vorticity is proportional to how far you are away from the origin squared. All right, so we'll go to the last page, and we'll keep going with example 3, and that was f is equal to negative sine theta cosine theta, which we write as negative y over root x squared plus y squared, x over root x squared plus y squared. So now comma 0. All right, so we need to put a comma 0 there. We're in 3D. All right, so now we just have to compute then the divergence. So is this fluid compressible, or is it incompressible, or something like that? So let's compute that enough. So easy enough to do. We can easily see then the partial of the first one will be 2x y over x squared plus y squared to the 3/2 power, and then there'll be a minus there because there's this minus y sitting there. All right, and then we're going to go plus. It'll be 2x y over x squared plus y squared quantity 3/2 to the power 3/2, and of course plus 0 for the final term because there's 0 there, and that of course is 0. So we have an incompressible flow. All right, so there's a few examples about now our new tools of the curl, which is the cross product of the gradient operator times the vector field, and the divergence, which is the dot product of the gradient with f. And they are these wonderful descriptive tools to talk about what goes on with vector fields, particularly related to their expansion or their compressibility and their rotational. So rotation and expansion. Those are the key words here that describe vector fields. And we talk about curl-free or rotational, irrotational fields. We're talking about fields that have a curl of 0. And if we talk about an incompressible field, we're talking about one where the divergence is 0. So thank you very much.